Welcome everyone. My name is Germán Eizaguirre. I'm a PhD student at the Universidad Rovira i Virgili, and today I am presenting my work during my Cloud Star stay at IBM Zurich Research, um, which was motivated partly also by another European project, which is Cloud Skin. And so at the beginning of it, okay, wait, it's not passing. Okay, there we are. So it all began with this metaspace metabolomics annotation pipeline, which is a data analytics pipeline developed by EMBL, which is the European Molecular Biology Laboratory. And this is part of the Cloud Scheme project because it was first brought into the serverless in a previous project. And then we had the goal of optimizing its resource provisioning and also its overall performance in terms of execution time. So we worked on methods for optimizing both things with this kind of resource provisioning models. And so what we saw is we began with its pre-processing stage or phase, which was basically two stages of connected calls of parallel functions, in which each stage communicated with the other through an object storage system, specifically ES3. And we saw that this put like a lot of stress in the intermediate storage, and it was limiting the execution time. And the optimization of the resources was not obvious or straightforward because we could not simply define a number of functions and put them at both sides because, as you can see at this heat map, the number of optimal functions for the parent stage, which could be the stage at the left, and the number of functions at the right was different. And there was kind of at least a slightly complex optimization problem here. So we worked on that. And what we saw was that as we have two stages with different computation times, and also as object storage systems like S3, for example, have usually asymmetric read and write performance, not so much in bandwidth, but more in throughput in terms of operations per second, we saw that we could model the performance of this preprocessing stage or phase, by predicting the I/O time of each configuration, the computational time based on the parallelism of each stage, and also the invocation time of the cloud functions. Because even if cloud functions are fast to invoke, they still usually have at great levels of parallelism. They usually need like 3 to 4 seconds to have all of them running. And so maybe having a great parallelism could affect the overall performance. And so what we proposed here, usually these kind of optimization problems in previous state of the art take the whole pipeline and try to optimize the whole pipeline in which several stages could take part. Like you could have, for example, 12 stages. What that gives us is a very complex problem to resolve because you have lots of variables and can be even an NP complete problem. So we tried to solve this with just local decisions in which at each stage we can measure exactly the I/O time we expect from each parallelism and also the CPU time, the computation time, and just take decisions online at each stage. Okay, and decide the parallelism of each stage as it comes. And so we developed this local optimization model in which we take the decisions online as a different option to the state of the art, which, as I said, does the optimization at end-to-end level of the pipeline. And we had, for this pre-processing stage or phase, we had like 10 to 25% faster results compared to previous resource provisioning models such as Jolteon, as you can see here, for different data sizes. And obviously what we are working on, and this is work in progress, but we are working on doing this first for the whole pipeline, the end-to-end pipeline. As you can see, we are just getting 10 to 25% improvements, but this is just the first part of the pipeline. We are expecting to have even greater improvements when we apply this method to the whole pipeline, and not only to this metabolomics pipeline, because resource provision in serverless data analytics is a whole domain and a whole research line, and we are trying to apply this also to more general purpose data analytics, obviously kind of standardized benchmarks such as TPS DS, but also other use cases that are being tested in the state of the art, machine learning pipelines, and also, for example, video analytics pipelines. And so we are working on it. Currently, it's work in progress, as I said, and we are trying to do research on that. And yeah, we will publish it soon, I hope, our final results. So thank you very much for listening. That was it. As I said, this was part of the Cloud Stars internship, but also of the Cloud Skin project. And also a special thanks to my supervisors at IBM Research Zurich, Bernard Metzler, but also Animesh Trivedi and Radu Stoika for helping me. Thank you.
Thank you. Any quick questions? Okay. Remember, you can always ask questions in Discord channel after the talks. Praveen, go ahead. Germán, make sure to stop sharing your screen.
Okay. Yeah, there we are. Yes. Is it okay now? Okay.
I think you're still screen sharing. Okay. Praveen, go ahead.
Hi, can you see my screen and hear me?
I can hear you and I can see your screen. Everything looks great. Go ahead.
Right. Hi, I'm Praveen, a recent graduate from the University of British Columbia. I'm presenting our work called Growlithe, which is a tool to help serverless developers with their data protection needs for access and information flow control in a fast evolving environment. Serverless applications process sensitive data today, like let's say financial and personal information, and they're gaining popularity as the cloud providers manage infra, easing developer burden. However, their same unique traits create data protection challenges. These applications are heterogeneous and use multiple languages, which complicates a uniform data protection approach. Unpredictable environments with shared containers risk data leaks across requests. Also, the complex and evolving applications with diverse sources increase the chances of bugs and misconfigurations. And short-running functions demand low overhead solutions. Cloud providers and tenants operate under a shared responsibility model today for security and compliance. Providers would secure the infrastructure, but tenants today are still responsible for handling access control and data protection needs. Cloud IAM tools exist, but these are platform-specific, coarse-grained, and often very, very hard to configure. Thus, they fall short for serverless-specific challenges. This is where we designed Growlithe to help serverless developers with their compliance needs. Given an application's source code and cloud configuration and a set of policies to enforce, Growlithe creates an updated application to be deployed that enforces these policies. However, this solution requires us to answer a few key questions first. First, where do you enforce policies in a complex application? How should a developer specify these policies for access and information flow control needs? And third, how should the tool enforce these policies with minimal overheads? To answer these questions, we broke down Growlithe's design into 3 stages. In stage 1, Growlithe creates a platform-independent data flow graph abstraction for serverless application using a 2-step approach. First, it would analyze each function's source code with CodeQL to build per-function data flow graphs, capturing intra-function data flow across resources. For example, read from an external S3 file and write to a local file. It then combines these graphs with inter-function dependencies parsed from the application configurations to form the end-to-end data flow graph. In the second stage, developers specify policies by annotating the edges of the data flow graph with a declarative specification language. These policies include access and information flow control policies to restrict data flows. Some examples would include restricting rights to a resource based on a region, or restricting rights to a resource based on some upstream data in the workflow. I would allow you to refer to the paper for details of the specification language. In the third stage, Growlithe enforces the policies using a hybrid approach. First, during static checks, a policy evaluation will result in either allow, deny, or can be deferred for runtime check if the policy requires some kind of runtime information. A failure at this stage is flagged to the developer for debugging before deployment. Then, during runtime checks, Growlithe generates an updated application by automatically instrumenting the source code with inline assertions if the policy depends on dynamic data. Note that this approach for runtime checks ensures that we do not need any change in the underlying infrastructure. This hybrid approach reduces the number of policies to be checked at runtime and allows enforcing policies that require dynamic runtime data, and thus it improves coverage as well. We evaluate Growlithe on several fronts, but I'll quickly summarize the performance, overhead, and scalability evaluation of Growlithe. We compared the baseline application with default IAM policies with two configurations of Growlithe. We saw that Growlithe with only the runtime enforcement added an overhead of around 28 milliseconds per function, whereas our hybrid approach added 23 milliseconds. Thus, we saw that hybrid enforcement leads to a 19% improvement in the function runtimes compared to runtime checks alone. To test the scalability, we used two micro benchmarks of linear chain and fan-out, as the typical workflows would fall between these two extremes. And we saw that the end-to-end latency overheads of Growlithe remained modest, scaling linearly in linear chain and sublinearly in case of fan-out configuration. Thus, we see that Growlithe scales well as the application grows. To wrap up, Growlithe integrates compliance into the serverless development lifecycle. It's portable across platforms, works across languages, and has modest overheads. It can be extended to new services and adapts to provide continuous compliance with updates to the application and policies. Please scan the QR code for the source code and full paper for more details about the work and our evaluation. Thank you.
Perfect timing. Please put the link to your, whatever QR code is leading into a Discord channel.
Sure.
No, to share it. And I have actually a very quick question. So did you consider that policy language and then static checks and so on to explain using AI? Like, if you want to make it easy for users to create policy.
Yeah, so we were discussing this. So of course, right now, our goal was to make it simpler for developers to specify policies, but still there is some manual work in our tool. But our thought process was, once we have this intermediate language, if we try to integrate it with some AI tool to automatically convert natural language to policies in our specification language, that can be a tiered approach to specify policy.
Sounds great.
We haven't done that yet.
Well, just ask AI to write the code for you, right? Vibe coding. Okay, Tomasz?
Sure. Okay, so I will try to share the screen.
I'm keeping my fingers crossed. Okay, looks like something is happening. I see your screen.
Can I change the slides?
Looks good.
Okay.
Motivation. So, go ahead.
Okay, so my name is Tomasz Szydlo. I'd like to present the work titled MicroFaaS, Adaptive Serverless Computing for Internet of Things. This work has been done by Growlithe and myself. It's my former MSc student. So the motivation of this research. IoT, Internet of Things growth is projected to exceed 40 billion of devices by 2030. These IoT devices are being smarter and smarter. They can process various types of data, detect frauds, predict failures, and they can offer other useful things. However, the intelligence for these devices is provided by the ML models and the complex algorithms that need to be deployed and executed on these devices. However, the main constraints are limited CPUs, memory, and the energy of these devices that you can use for processing the data. So there are different ways of overcoming this problem of limited resources on the IoT devices. First, for ML models, one of the approaches to optimize the models and the neural networks by pruning, reducing precision, or using techniques such as, for example, neural architecture search or knowledge distillation. Then these optimized models should fit inside the IoT devices and be executed directly on the devices. And this area of research is called TinyML. However, It's only possible only for limited types of the problems and algorithms that we would like to run on the devices. The second approach assumes that the models or the complex algorithms are moved from the devices to the edge or cloud, and then IoT device invoke them as external services. In this case, we have quite a large flexibility because these algorithms or the models can be deployed on the external servers, 6G multi-access edge, so on the GSM antennas, simply speaking, on-prem servers, home gateways, etc. But assuming that we have these models or the code deployed to various edge locations, the research problem is which edge instance should we select for the current invocation of the code and the model. So speaking of which, I would like to present our research outcome. So the complex algorithms of ML models to be executed can be run locally on the device, as we have discussed before, or can be served as a function by a FaaS function as a service providers. In this research, I'm presenting an adaptive framework called MicroFaaS that intelligently selects the best execution endpoint from the available ones using pre-trained execution time estimation models for each function and the FaaS platform. Without the pre-training phase, the agent on the device making the decision which endpoint should be picked for the execution would need to learn that at the runtime, causing some unpredictable behaviors at the initial stage. So it's exactly the same problem as we have in the reinforcement learning algorithms, where in the exploration phase, the system is to some extent unstable. So we wanted to avoid such a problem. So we are assuming that the predicted execution time for the computation is a sum of predicted computation time from the pre-trained regression model and the communication time, which is trained and updated on the device. So we are tracing all of the congestions and the network throughput along the line while in real time when the device is up and running. So MicroFaaS proxies store these regression models for the predicting execution times and share them across IoT clients, enabling a knowledge base about remote FaaS functions. Then the MicroFaaS monitors network connectivity and updates communication cost models dynamically on the devices itself. As an example, what I would like to discuss in the case study, so there is a very simple use case presented on the right-hand side. So the case study shows that the MicroFaaS subjects the decision of offloading the computations to the external FaaS based on the network congestion. For a congested network, the invocations are offloaded for much heavier task sizes compared to when the network is not congested. So we can see two decision points for the congested network on the right and for in the normal situations on the left. The difference is because the transmission time in the congested network is much longer than in the ideal network conditions. So based on the network traffic, the agent on the device picks the proper proper time for uploading the task from local execution to the remote FaaS one. To sum up, MicroFaaS, so to sum up, results show that the pre-training the execution time models significantly reduces initial system calibration time and improves adaptability to changing network conditions. The proposed approach demonstrates improved performance by dynamically selecting the most efficient environment per invocation, ensuring faster, more reliable execution even under network degradation. In the experiments, the execution time of benchmarks has been significantly reduced to 68% of the time taken by a naive strategy that offloads all of the tasks to FaaS, and to 5% of the time required when all tasks are executed locally on the device, on the IoT device. Simply speaking, because the IoT device was quite slow for running the benchmarks for a long time. And the framework is cloud agnostic, allowing seamless integration with multiple FaaS providers. More details you can find in the FGCS paper just accepted to the journal. So all of the experiments and the links are provided in this paper. So thank you for giving me the possibility to present the outcome of the research. And of course,
Thank
if you
you.
have any questions, I'm open to.
Thank you, Tomasz. Any questions to Tomasz or to any other presenters? Okay. Remember to unmute yourself if you are asking question. I actually have one question. If you go just to the previous slide. Yes. So that's like lot of asking for developers, like could it be like vibe coding for MicroFaaS? You know, just give me a function and then run it or find the optimal execution in all those, you know, target IoT devices I want to run. Do you think that is possible? Like, you know, you do some profiling or whatever, and then user says, I want to run that function, and it just figures it out.
This was the idea in this research. So we have some tools that you can create the serverless function. You can create the function, then you can deploy it on the FaaS, and then the benchmarking process has been automated. But at the time we had to, at the time of doing this research, the vibe coding was not as popular as it is now. So simply speaking, we had to implement the service function. But with the vibe coding, we can try to do it. So we can first ask LLM to code for us. Then we can automate the deployment. And we have script for benchmark for this pre-training and learning the execution models. So I think it's doable. And I think it's a future that we'll just ask LLM to create the code for us, doing some goals and so on, you know, following some ideas and so on and so forth, solving our tasks. And then we can ask, I believe, LLM to deploy it. And then we can ask it to profile the execution times. So I hope that we'll see such solutions in a short future.
Yes, kind of AI agent to do all of that hard work for you and just tell you, you know, success. Okay, any other questions? Okay, we will have a 5-minute break or maybe 6 minutes to, you know, 10 minutes after hour, start the last session. And